So let's first talk about how we can quantitatively measure the transient of a linear time invariant system. So it's very similar to, for instance, when you look at a car, you wonder how fast you can go from 0 miles per hour to 60 miles per hour. This is basically this 0 to 60 time, acceleration time, is basically a quantitative measure for a transient response of a system. But now the system is just the car, the speed of the car. So in general, what measures do we have? Just to illustrate this, let's consider the following scenario. Let's assume I have a linear time invariant system, and let's say in general it will respond to a unit step. So this is our unit step response, keep in mind, for a asymptotically stable system. So what's going to happen is, for some system we'll go from 0, since this is 0 state response. So go from 0 and eventually decay to 0. Decay to the steady state. Now, and we can already see there are several things we can do to evaluate some of this, right? For instance, we go from 0. Now, how fast it takes to reach the peak? This is the peak time. Okay, and we sometimes use t sub peak to denote it. Just the first most straightforward thing to see from the graph. T peak, and it's time to reach the maximum of your output signal, y of t. So this is y of t, the response. Secondly, well, you want to know, well, how high is this maximum? But you don't really want to compare this with 0. You want to compare how this maximum is different from your steady state level. This is what is called the overshoot, OS. And is usually valued in terms of percentage. So it's the max of y of t minus the steady state of your output signal divided by, or normalized by, the steady state value times 100%. Okay. So apparently here is YSS here. This is the steady state level right here. Very straightforward. And sometimes we'll also want to look at, well, this is my steady state, right? I can define a 10% of steady state here. And let me move this up a little bit. So this is YSS. I can also define a 90% level of my steady state value. And I want to see, well, here to here, this is 90%, this is 10%. I want to see how much time do we need to go from 10% of my steady state level into 90%. This is sometimes called the rise time. TR or T rise is the time that your response y of t goes from 10% of your steady state to 90% of your steady state. That's like, from 0 to 60 miles per hour, how much time it takes. But this is only the initial rise, right? And after that, we see if you follow, this is your initial rise. But also there's some oscillations, although the oscillation will be decaying. And what do you really want to see is how fast does it take such that the oscillation is negligible, or y of t is very close to the steady state. This is what we usually call the settling time. T sub s. And T settling time is usually defined as the time that needs for the system to reach plus minus sometimes 2%, sometimes 5% of your steady state level and remain within this range. So let me write it. This is settling time. Ts. It's the time for y of t to reach and remain in plus minus 2%, or as I mentioned, sometimes 5% of the steady state level of your output. Okay. And these are the four most commonly used performance measures of transient response, especially when we look at the unit step response. So let me repeat: peak time, percentage of the overshoot, the rise time, and the settling time. For simple systems, it's possible to calculate all of these measures using closed form formulas. We have formulas to do that. For more complicated systems, it's almost impossible to calculate them using these formulas, or even very difficult to derive those formulas. In those cases, we have to resort to other tools like simulations to help us figure out how this can be done. Okay. So this is the quantitative measures. Now, when we define this, let's look at some examples and see how they can actually be defined and more quantified. So what we'll do, let's start from the simplest systems. Okay. Now let's look at first order systems. Nothing can be simpler than a first order system, right? So let's start with the first order system. So linear time invariant, and the system has to be stable, right? And we're gonna use a very special form of my transfer function. So the transfer function is 1 divided by t, which is a constant, t times s plus 1. The way I define this like that is because the DC gain is equal to, when you plug in s equal to 0, the DC gain will be 1 divided by t times 0 plus 1, and will be equal to 1. So you have unity DC gain. This is kind of a very standard form of the system. Now, you have input for output, and since, remember when we talk about transient, we want to focus on unit step response. So my input signal here will be unit step, and in the frequency domain, Laplace transform will be 1 over s. My output y of s will be 1 divided by s times 1 over ts plus 1. Now let's just pause for a second and think about the stability, right? The characteristic root of the transfer function is the s such that ts plus 1 equal to 0, or s equal to minus 1 divided by t. And if we force t to be a positive number, then we know this one will be negative, or the system will be asymptotic stable, and there will be nothing to worry about. And we can proceed and do all the calculations, and we know there's going to be a steady state. The system's not going to blow up. So let's now continue. And apparently this can be rewritten, since we want it to look a little nicer. So we divide t on both sides of my transfer function, numerator becomes 1 divided by t, and denominator becomes s plus 1 over t. This is the numerator, 1 over t. And now it's the natural form we can apply our partial fraction expansion method, or the cover-up method, if you will. And we know it's going to have two terms. One look like this, and the other one looks like this. Okay, and you use cover-up method. It's very easy to obtain that k1 will be equal to, so you cover s, and then k1 will be equal to 1, and then k2 you do the opposite, right? And k2 will be negative 1. Okay, k2 will be negative 1. And if you put things together using the partial fraction, then this will give me y of s equal to 1 over s minus 1 over s plus 1 over t. So this is the Laplace transform in the frequency domain. And if you want to convert this back into time domain, we have y of t equal to 1 minus e to the negative t over capital T. Now, from 3101, we usually want to multiply this with the unit step signal, but if, let's say, we only focus on t positive, we don't really have to write the unit step signal anymore. So this is the time response, this is the transfer response. And we can talk about this, a few things. The first thing is, right, when t goes to infinity, when t goes to infinity, the exponential term in the response will go to 0. E to the negative t over t will go to 0. And y of t, sufficiently large, will be equal to 1. And this conclusion matches our earlier result that the DC gain is unity. Right? You have a unity DC gain. Meaning, in a steady state, the unit step response should have the same magnitude or amplitude as the input, which is equal to 1. Right? And we have both unity amplitude at the input and unity amplitude of the output signal. Okay? This is the first thing we can. Second, let's maybe graph this y of t, which will be easier, and we can match what we have with the previous discussion on the quantitative measures. Now apparently I'm looking at only this 1 minus exponential decaying signal. Is not too difficult, and you have done this also in 3101. Right, this will look like this, an exponentially decaying signal, and will approaching 1 as t goes to infinity. Okay. Steady state value being 1 that we just calculated here. So if you look at this, what is the maximum of y of t, right? We need the maximum to answer my overshoot. So let's go up again. The 4 measures, how much time it takes to reach the maximum. And the maximum, how different is the maximum compared to your steady state? That's the peak time and the overshoot. Okay, how much time it takes to rise from 10% of the steady state to 90% of the steady state? And how much time does it take to settle and would reach and remain within plus 2% of the steady state level? But if you look at this, the maximum of y of t is equal to 1, and this is on t go to infinity. And this is also equal to your steady state. So the way we define the overshoot mathematically is how much larger your maximum is compared and normalized to the steady state. In this case, it's equal, so the overshoot will be 0. There's no overshoot, or 0 overshoot. In the front graph, it's very straightforward, very intuitive, because it doesn't go up. It doesn't go above the steady state level, so there's no overshoot at all. Now, if there's no overshoot, what about the peak time? How much time does it take to reach the maximum? In the front graph, it's clear it takes infinite amount of time for the curve to reach the steady state, or the maximum value 1. So t peak will be infinity. And usually, if this is the case, we really don't have to, put too much energy into the discussion of the overshoot and the peak time for the first order system, because they're so obvious. It's a little trivia actually to look at it. Okay. But we have two others. We have the rise time, and we have the settling time. Let's look at the settling time, which is relatively easy to calculate, since the curve we have here is monotonically increasing, right? So it only becomes larger and larger. If you want to calculate the settling time, you only need to find 0.98 and see where this one is located. That's my settling time. And if you want to find rise time, you find 0.1, you find 0.9. Okay. And you calculate the difference from these two spots, and that will be your rise time. So let's start with the settling time. So how to calculate the settling time? That will be what? From this graph, I want to have 0.98. Should be equal to 1 minus, should be equal to, let's do this step by step, should be equal to my output when t is equal to my settling time. I will solve for settling time, but I can plug that into the equation of y of t. So 1 minus e to the negative ts over capital T. And also it's easy, it's equivalent to e to the negative ts over t is equal to 0.02. And one more step, you take the logarithm of both sides. Will be like this. So it means your settling time system to a unit step input signal will be ts and t times logarithm of 50, since 0.02 is 1 divided by 50, and we want to take care of this negative sign here. And the best way is to take the reciprocal, so 0.02 will become 50. Okay? And you see the negative sign disappear. Now if you use your calculator, you'll find out, if you type in logarithm of 50, you'll find it's approximately equal to 3.912 is the logarithm of 50. And of course we have this capital T. And of course, sometimes we say, well, this is approximately equal to 4. Since 3.9 is close enough to 4. Now, this is a rule of thumb. And since this capital T becomes so useful in addition to being just a coefficient in your transfer function, right, T is the coefficient here, it also appears as a measure of time, at least in the settling time. People give it a special name. This is usually called the time constant. And if you look even closer, this t appears in your exponential function like this. E to the negative t over t. Okay. So its t is also associated with how fast the exponential signal will decay. and it carries a lot of physical meaning that we'll discuss, later. But as far as the name is concerned, we sometimes call this capital T when it appears in this form in the transfer function, or it appears like this in your exponential signal. We call this capital T a time constant. Okay. So for example, if we do an example here, if we have a transfer function to s plus 1, right, the time constant will be 2, right? This 1 divided by 0.1 times s plus 1. And your time constant will be 0.1. And so on, right? For instance, if you look at exponential signal e to the negative 0.5t, our time constant will be what? Will equal to 2, since 0.5 times t is t divided by 2. Or you want to put the time constant in the denominator as you have it up here. As you have it up here. Now, I can also ask, what about this one? E to the 0.5t. See, there's no negative sign in front of this exponent. And this exponential function will blow up to infinity. Okay? It doesn't belong to an asymptotically stable system. And the time constant here simply doesn't exist, because this guy represents something of an unstable system or unstable node. We blow up to infinity, this time constant just doesn't make any sense. Okay, so this is the rise time. I'm sorry, the settling time can be calculated rather easily. Now let's do calculation of the rise time, which is also quite simple. So rise time, right? To calculate rise time, you need to calculate how much time it takes to go from 0 to 0.1 and 0 to 0.9, and then you take the difference of the two. So we calculate these two things. We calculate the 2 points. The first point, t1, 1 minus e to the negative t1 over t, and we let it equal to this 10% point. And the second time point, we have the signal goes to 90%, so 0.9. And then of course the rise time will be t2 t1. And to calculate t1 and t2, basically you could use the same methodology, right? t2 will be equal to what? It will be t times logarithm of 10. So you have 1 minus 0.9 will be 0.1 and took the reciprocal. t1 will be t times logarithm of 1 over 0.9. Okay, so 1 minus 0.1 will be 0.9, and take the reciprocal again. So tr, the rise time, will be the difference of the two, t times logarithm of 10 minus logarithm of 1 over 0.9. And you apply a little bit of the knowledge on logarithm, so minus 1 over 0.9 will be logarithm of 0.9. And you put this together, will simply be logarithm of 9. Okay. Which is 10 divided by 1 over 0.9, or 10 multiplied by 0.9. Okay. This will be, basically your either first year calculus or high school algebra should take care of the logarithm calculation, but this is the procedure. And we can punch in again logarithm of 9 into a calculator. This will be approximately equal to 2.197 of t. So roughly, 2 time constant is the rise time, 4 time constant is your settling time in terms of the first order system. So three important concepts. Sorry, three important calculations, one important concept. The concept is the time constant. We should have mentioned this in 3101. If not, this is something that keep in mind. Secondly, how do we calculate settling time? The procedure. How do we calculate rise time? And the most important thing is the rule of thumb. First order system, settling time roughly 4 time constant to reach and remain within plus minus 2%. And rise time from 10% to 90% of your steady state level, the rise time will be roughly 2.2 time constants. Okay.